Hey there, I'm DevPoodle. This is a guide on Godot's Compositor, and more specifically, on making Compositor Effects. These give you far more control over Godot's rendering pipeline than other forms of post-processing, and so are an invaluable tool when you're trying to make something more complex. But first, what is the rendering pipeline? In practically all game engines, rendering, the process of drawing pixels onto the screen, happens in multiple steps. Godot uses a process called forward rendering, which makes this pipeline much more condensed than in a lot of other programs. It's only 4 main steps. First, opaque objects are drawn. Opaque meaning objects that are completely solid. You can't see through any part of them. Second, the sky is drawn and put behind everything else. Third, back buffers are copied, and some effects like screen space reflections are applied. If you don't really know what that means, don't worry, I don't either. And finally, transparent objects are drawn. If you can see through any part of the object, then it would be considered transparent. So often foliage or glass would be rendered here. A lot of data is passed along between each step. The most obvious example would have to be the color buffer. This contains the final image that will be rendered to the screen. But there are a few other important buffers as well. For example, the depth buffer, a texture that indicates how far away everything is from the camera. This is often used in fog or water shaders. And the normal buffer, a texture that stores information on which direction each polygon on screen is facing. This is used for a lot of common lighting effects. What Godot's Compositor allows you to do is manually create your own step in the rendering pipeline in the form of a compositor effect. You get to choose where exactly your effect goes, and use any of the buffers I've described in whatever way you want. Even better, you can add as many effects as you'd like. If you're willing to put in the effort, you can practically make the whole rendering pipeline your own. So, let's make a custom effect. I'm going to keep this really simple for now. First, create a new empty script that overrides Compositor Effect and has its own class name. You can make this a tool script if you want to be able to preview the effect in the editor. We need to create member variables to store various rendering-related objects. We'll need access to Godot's rendering device. This is the API that will allow us to run compute shaders. We'll also need to store a compute shader and its corresponding compute pipeline. These are how we will go about processing our effect. Then we implement the init function. Here we need to initialize the shader and pipeline using a shader I've called computeshader.glsl. Don't worry, I'll go over how to write this soon. With our initialization done, we can get to running our effect. All processing happens in the render callback function. Here we're given 2 parameters. Callback type is a number representing when the effect is being applied. Here's the numbers corresponding to each location in the rendering pipeline. You can use this to make sure your effect is being run at the right time, although the shader we're going to write can be placed at any point in the pipeline. The other parameter, render data, provides us with all the information and rendering objects we have access to. From it, you can get 2 main objects, render scene buffers and render scene data. Render scene buffers contains all of the data I was just talking about earlier, like the color, normal, and depth buffers. Render scene data mainly gives you information about the camera, like where it's located, its projection, and some stuff related to VR rendering. I'd highly recommend reading the doc pages on all of these classes, if you really want to know everything that a compositor effect can do. In our callback function, let's first get render scene buffers. Using that, we can also get the resolution of our viewport. As for buffers, this is going to be a simple shader, so all we'll need is the color buffer, which we can get like this. First, we create a new RD uniform, specify that it's going to be an image, and give it a binding. A uniform's binding is a unique number for that specific uniform. You can set it to whatever you want, just make sure to never set 2 uniforms to the same binding. And finally, we add the RID of the main color layer from render scene buffers. Then we bundle all of our 1 uniform into an array. Before we can dispatch our shader, we need to calculate the amount of shader groups we want to run. This will cause our shader to run once per pixel in our viewport, which is what we'll need. And we can finally run our shader. We create objects for our uniform array and our compute list, which is basically a list of compute shader related instructions to be sent to the GPU. Then we go through, bind everything, and dispatch our shader. Oh, we also need to make sure to free our uniform set now that we're done with it. And that's it for the script. It might have required quite a bit of explaining, but in total it's only around 40 lines of code. Next comes the compute shader itself. Now, I already made a video on compute shaders that goes into quite a lot more detail, so I'm going to skim through some things. If by the end you're still confused, I'd recommend watching that after you're done with this one. Let's open up an empty file that will contain our shader. I'm using Visual Studio Code to write this purely out of convenience. You could also use Notepad or really any text editor of your choice, it doesn't matter. First, we add a heading specifying that this is a compute shader and that it uses version 450 of GLSL, which is the primary shading language Godot supports. Then we specify something called the local size of the shader. Basically, this gets multiplied with the group size we decided on earlier to determine how many times our shader should be run. If you multiply it out, you'll see that this gets run once per pixel. This isn't the most efficient way to do it in practice, but it's fine for now. Again, this is not really a video on compute shaders. Then we declare the color buffer uniform we're passing in from the script. Remember the binding we set earlier? That should match the binding value here. Then we can define the main function that will get called for each instance of the shader. Here's a basic shader to get you started. It gets the screen UVs using GL Global Invocation ID, which is a variable all compute shaders have access to. It uses that to load in the color of the corresponding pixel in the color buffer. Then finally, it calculates that color as grayscale and writes it back into the color buffer. When it comes to coding in GLSL, most of the basic syntax will be exactly the same as a regular Godot shader. So if you've written one of those before, you should be good. Back in the engine, how do we actually apply our compositor effect to our scene? First, create a new environment node, or in my case, reuse the one you already have, attach a new compositor to it, and then add your effect to the Compositor Effects array. From the options of your effect, you can enable or disable it, change when the effect takes place in the rendering pipeline, and tell Godot that you'll need certain extra buffers. The normal buffer, for example, is not included by default. You need to enable this option to get access to it. With our effect added, if we run our game, we should see this. Our compositor effect is turning everything grayscale. If we change our callback type to post-opaque and run it again, well, before we do that, I'd like you to make a prediction of what you think will happen. This is the diagram of the rendering pipeline, and here is where a post-opaque compositor effect will run. What do you think the final result will be? Feel free to make a guess in the comments. Done? Well, here it is. The effect is only being applied to opaque objects, leaving the sky, which gets rendered afterwards, and partially transparent objects still in full color. Also, sorry for getting all Dora the Explorer on you there. Now, this wouldn't be a very good guide if I didn't at least cover a few of the other buffers you have access to and how to use them. There are 4 main buffers you might want to use in your effects: color, depth, normal/roughness, and motion. I'll show you how to use depth and normal roughness, mainly because I haven't actually used the motion buffer much, and I don't want to accidentally put out any incorrect information on it. So in our script, we first create 2 new member variables to store samplers for the depth and normal textures. Samplers are basically a collection of settings telling the GPU how it should read data from a texture. In the init function, we then initialize these with the default sampler state. In the render callback function, we will have to pass a little more information to our shader to be able to use the depth buffer properly. Specifically, we need to pass the viewport size and the camera's inverse projection matrix. I know it looks a little complicated, but I think this is the way to do it in the fewest lines of code. Honestly, I'll probably have to make a whole video on passing data to compute shaders eventually. Here's how we'd format all that data into a single packed byte array. We create 2 new RD uniforms, similarly to how we made the color uniform. But these 2 are samplers. And remember, make sure to give them all unique shader bindings. Then you can add them to the uniform set array. Before dispatching the shader, we'll pass this along as a push constant with this new line. Next, we need to update the shader. First, we define what data a push constant will contain, which is the camera's inverse projection matrix, and the viewport's resolution. Then we'll declare the depth and normal texture uniforms, similarly to how we declared the color uniform. I don't mean to sound like a broken record, but again, make sure the bindings match what you wrote in your script. Down to the main function. Because our depth and normal textures are samplers instead of an image like our color texture was, we'll need to normalize our UVs by dividing them by the size of our viewport. From here, you technically can just sample your depth or normal textures directly. Here's what this looks like in code. and here's what they look like rendered to the screen. But this isn't really the proper way to do it. You see, both of these textures are stored in special ways. The depth buffer represents how far away an object is from the camera, but it doesn't do this linearly, and is all stored in the range from 0 to 1. As an example, if you sample the pixel 1 unit away from the camera, the depth buffer will not store a 1 in that position. To get the linear depth, you have to convert the output using this function. Most of the effects I've made that use the depth buffer use linear depth, so I pretty much always include this function in my compute shaders. I'd recommend reading the Godot docs page on advanced post-processing. That's where I got the function from. The normal buffer is also stored strangely. To access it properly, you're meant to use this function, which is included in the Godot Compositor Effects documentation. Oh, and if you're curious, because this is outputting a vec4, the x, y, and z values represent the normal vector, and the w value represents material roughness. With both of these helper functions defined, we can now properly use the depth buffer and normal buffer in our shader like this and like this. Unlike the color buffer, we cannot write to these because we're using them as samplers instead of as an image. I figure it isn't really enough to showcase just how to make one simple compositor effect. But I also can't exactly give a step-by-step guide through a bunch of common effects, because then this video would be like an hour long. So instead, I've made a library of compositor effects you can look through in the description. Let's quickly run through them. The first is Sample Effect. This is pretty much the exact effect I just made in this video, except instead of turning the screen grayscale, it just renders out a buffer of your choosing. In the effects exports, you can set which buffer you want to render to the screen. If you're making your own compositor effect, I'd highly recommend starting with this as a base. Outline. This effect has an outline around all objects. To add the outlines, I compare nearby values from the depth buffer. If there's a significant difference, I know we're on the edge of an object, and so I paint the pixel black. Pixelate. This effect pixelates the entire screen like I did in my video on making a pixel art shader. It also adds an outline around objects and a highlight along object creases. For the outline, I used the same technique as the previous effect. For the highlights, I use a similar method, except I compare differences in the normal map instead of the depth map. Raytracing. This effect completely overrides the color buffer, rendering a few colored ray-traced spheres. A lot of the shader code here is inspired by Sebastian Lague's video on the subject, which I'll link in the description. I plan on making a full video on ray tracing in Godot, but no spoilers, at least for now. Actually, if you look through the source code of the ray tracing example specifically, you'll notice that I'm not using Godot's native Compute Shader API. I wrote an abstraction of it a few years ago called Compute Shader Plus. I still find it quite useful at times, so feel free to try it out. It's on the Godot asset library. A link to the Compositor Effect library is in the description. I hope I've taught you everything you need to know, and given you enough resources to get you started on making your own compositor effects. Feel free to like and subscribe, and of course, if you have any questions or suggestions, let me know in the comments. I'd also love to hear about what effects you end up making. I'm DevPoodle, I'll see you later, and goodbye!